Nanjing University, and he'll be talking about understanding the Linux kernel visually. This is also one of the best student papers.
Okay, thanks for your introduction. So I'm Hanzhi from Nanjing University. Today, I'm glad to share with you our work that provides a novel perspective for developers to debug and understand the Linux kernel. So we all agree that the Linux kernel is a critical software system, right? It is widely used in cloud servers, embedded devices, and desktop PCs, and so on. So for kernel developers and system researchers like us, it is common to debug the Linux kernel for reasons such as maybe to diagnose a kernel panic or to figure out how a specific kernel component works. So let's start from a simple case, maybe. You can imagine that you are a beginner and you have some basic knowledge about the Linux kernel. Now you want to figure out how the process scheduler works in the real kernel implementation. So you might debug the kernel step by step and imagine that you have paused the program execution at a point, and now you want to know what is the next thread to be scheduled. Is the process scheduler work as the textbook says? So how do we debug the kernel? Of course, we use GDB, right? With GDB, we can pause the execution at any program point and to inspect the value of any variable in the memory at this time. So, of course, GDB is powerful, and we can use it to complete almost any interactive debugging task. But however, just to get the next thread to be scheduled, we have to write complex script like this, even with the modern Python extension support. So as you can see, we have to rely on CPU RQ, container of, such complex kernel macros to unwrap the kernel data structure step by step until we finally get the thread we want. So actually, such script is really hard to maintain and error prone. Here is actually a bug here, and in GDB script without the support from code editors and compilers, such bug will be really hard to find. So kernel debugging is still difficult because that it is non-trivial to explore the program state of the Linux kernel, even for simple tasks, just using GDB. So things can become even worse when we face real-world problems. So this is a simplified trace of a famous kernel CVE. So it is a concurrent use after free bug, and its root cause is that one CPU hold a wrong lock when it is trying to free an object. So as a result, when CPU 2 is traversing the data structure and it fetched the node, so before it's access to that node, CPU 1 can mark that node as dead. And in the background, there can be a kernel thread that free all the nodes that already been marked as dead. So as a result, CPU 2 will face with use after free. So this is a typical concurrency bug, right? However, such bug take to kernel developers nearly 2 weeks to reach a consensus on how to fix this bug. So why it is so challenging? The reason is that this bug actually involves various kernel-specific mechanisms, such as the maple tree, the RCU synchronization, and the slab allocator. So to diagnose this bug, one has to understand how these mechanisms work. So this is really not non-trivial. So we take the maple tree as the example to see why it is challenging. So the maple tree is a new type of B tree introduced in Linux 6.1 for efficient process address space management. So when we talk about a B tree, what will come to our mind first? So maybe it will be an intuitive figure like this, right? It provides an intuitive visualization of the data of the internal structure of the maple tree. However, when we want to inspect the runtime state of the maple tree during the program execution, what GDB can provide us is just a textual dump like this. This is really hard to read and understand. So don't forget the maple tree is used to manage the address space. So when we talk about this, something comes to our mind will be a rectangle like this in our OS textbooks. However, the real kernel runtime state is so large and complex. It is not trivial to explore the state and extract this address space from this. So this is that GDB can provide limited help. So it is non-trivial to export a specific part from the kernel state, right? So the challenges to understand and debug the maple tree actually roots on the complexity of today's Linux kernel. Its program state is really large and complex, and we have to spend a lot of effort to simplify it and match our mind, that is, to find what we actually need from this mess. So the question will be that, is there a mechanism that can help us efficiently simplify the kernel state in a customizable way? So I'm standing up here, so of course the answer is yes, right? So let's start from the full runtime state of the Linux kernel. So how can we simplify it to get what we want? So first, we can find that most part of the kernel state is irrelevant to our task. So yes, so we don't need it, right? So when using GDB, actually we have implicitly pronged most of the data, so only keep the useful ones. So for this example, we will not print the data of the entire process, but only the files and objects that of our concern, such as the PID, the process name, and the process memory manager. So we can model such prong operation as the object declaration. We can explicitly declare what we want in our DSL, such as the files, the objects, and the pointers that are related to the maple tree. So through this way, we can simplify the kernel state and help developers to focus the objects that only related to our task. So secondly, due to the complexity of the Linux kernel, the relation between two objects sometimes can be a long pointer chain, and such chain will cross many intermediate objects that might be irrelevant to our debugging task. So when we are using GDB, we will ignore such intermediate objects, and we are only concerned about the source and the target objects of such a long pointer chain. So we can also model this flatten operation in our object declaration. So assume that we have declared three objects, the task, the memory manager, and the maple tree. So they are connected through the links, that is actually the pointers. So we can use a dot connected expression to flatten this long data path, just as developers have done in the GDB. So in this way, we can help developers focus on the object relation itself, but not the irrelevant intermediate objects. So finally, we know that the data structures are used to manage objects in a logical order. For example, the maple tree actually manages the virtual memory regions in the order of their starting address. So sometimes we are not concerned about the internal implementation details of the maple tree, but only the objects they managed. So actually, the Linux kernel 6.1 have already provided a debug function to help developers traverse and print the nodes of the maple tree, but not the internal nodes of the tree. And so we can also model this two operation, right? So assume that we have constructed the maple tree using the DSL, and now we have its root object in the task struct. So we can use a converter function to extract a specific type of objects from this data structure. In this example, it's VMware struct. So, and we can remanage these objects in a more compact format, such as the array or maybe an unordered set if you want. So we modeled the prong, flatten, and these three simplification operations to a domain-specific language, that is the view construction language. So now we can modeled the kernel state as an object graph, where the objects are nodes and the edges are pointers. Through this way, developers can efficiently simplify the kernel state to get the customizable views and to get the views that matches our mind. So okay, now we can efficiently simplify the kernel state now. However, there is actually still a gap between us and efficient kernel debugging. So this is because that developers can debug the Linux kernel for various tasks, and these tasks can change during the debugging session. For example, we may or may not be interested in the internal implementation of the maple tree, or as a debugging session goes on, we may find that only the writable memory regions are related to the bug we are diagnosing. So then this cannot be determined before the debugging session started. So when using GDB, we have to either rewrite the GDB scripts on site or to provide some multiplexing functions that use arguments that can matches our changing needs. So actually, as you can see, such scripts is really hard to maintain and it's not flexible enough for efficient kernel debugging. So to solve this problem, we first enable ViewCL to define multiple views for each object. For this example, we can define a show MM and a show AS to display either the maple tree or the address space as the developers want. So in this way, we can understand one kernel component from multiple perspectives. So secondly, we provide another mechanism to flexibly customize what we actually want during the debugging session. So let's see, to customize what we plot for each object. So we actually define a table where the keys are objects and the values are the displaying attributes of each object. So to flexibly update a table, why not use SQL, right? So ViewQL actually provides a simple SQL-like syntax where developers can easily to select a set of objects that match some provided conditions and to update a set of objects and update their displaying attributes to customize how to plot them. So as a real example, we can select all the VM area structs that are not writable through a select statement, and now we can update this selected object set to set them as trimmed. Through this way, we can trim all the non-writable memory regions, and we can get a simplified graph that there are only 6 writable memory regions, which is really efficient for developers to diagnose a certain bug. So in summary, our solution is a 2-layers abstraction. We propose 2 domain-specific languages, ViewCL and ViewQL, that works together to break down the complex kernel state to simplified and readable views in a customizable way. So, okay, actually there's one more thing. So let's forget the paper for a while. So we can imagine what is an ideal debugging be. So maybe when we are debugging an ideal way, we want to inspect the program state. So when we can just talk to the debugger, so please provide only the writable memory regions of the current thread. So it will give us the view that we have described. So actually, our works have one step more near to that ultimate goal. So thanks to the simplicity of ViewQL, so we can easily synthesize the ViewQL programs with the help of large language models, and we just use a simple prompt to fine-tune it. So in this way, we can just talk to the debugger and to customize the views that I have already created by ViewCL. In this example, it is just we say, provide the writable memory regions, and the views are already created by ViewCL, and their displaying attributes will be flexibly changed. So we implement our idea in a prototype tool called Visual Linux. It consists of 2 parts. There's a GDB extension and the visualizer front end. In the GDB, we provide some new commands to plot, to extract the views from the kernel runtime state and construct the views. So in the visualizer front end, it receives the views generated by ViewCL, and it provides the ViewQL and the natural language interface to customize the views during the debugging session. So let's take a demo. Let you see how it works. So we start the Linux kernel with GDB email. This is a typical kernel debugging practice, right? And we have preset a breakpoint. Now the kernel is paused as there. So now we use a simple vplot command to pass it with a ViewCL source code, and now the view will be in time visualized in our front end. So in this example, this is the process scheduler run queue of 2 CPUs. So now we can also talk to the debugger through a WeChat command. Now we can tell it. In this example, it is to share the detailed scheduling info of a specific process. So now it will be translated to ViewQL programs and applied to our views. So now we flexibly change the display views as we want. Okay, we can also set the view of the task itself to tell it to say, oh, you to display the compact version of the address space. Now we get this address space, but not the red black tree. So, okay, so to evaluate the usefulness of Visual Linux, we evolve a classical textbook that is understanding the Linux kernel to the newest kernel, Linux kernel 6. So, such book covers various kernel components such as the file system, the address space, and so on. So, it has served a generation of kernel developers. However, it is based on Linux 2.6, and most of its figures and contents are outdated today. So we revive some representative figures in the latest kernel runtime to show that the Visual Linux is able to handle various kernel components. So, our evaluations show that the programming effort of VUCL is acceptable, and most of the figures can be created within no more than 100 lines of code. And also note that these code lines are counted independently. The code sharing will further reduce about half of the code. So we also find that most of the kernel data structures or components has evolved significantly. So about more than 80% of the data structure have under this significant changes. So to evaluate the performance, we run Visual Linux in two typical debugging environments. That is the GDB with a QEMU and the KGDB with an embedded device. So we provide a workload that is specifically designed that it creates multiple threads to obtain different kernel resources. So the result shows that Visual Linux performance is acceptable for interactive debugging. So in summary, we provide the first debugging framework to customize, to simplify the kernel state and customize the views as we want. So that's all of my talk. Thank you.